In this video, we'll talk about Gram-Schmidt orthonormalization process. Before we move into the Gram-Schmidt process, we first talk about projection operator. As you can see in the screen, this is how the projection operator is defined. First, let me talk about the notation first. This is called the projection of V in the direction of U. Okay, so if U and V be two vectors, then projection of V in the direction of U is defined as follows. This is the inner product between U and V divided by inner product of U and U multiplied by the vector U. Okay, now I have already talked about the inner product and outer product in my previous video. I'll drop the link in the description section. If you forget about the definition of inner product, let me remind you. The inner product between two vectors U and V is defined as follows: U transpose V. Okay, this is nothing but U1 V1 plus U2 V2 plus UN Vn. So this is how the inner product between two vectors are defined. So if we know the definition of the inner product between two vectors U and V, obviously U and V have n components here. So basically U transpose, or rather U transpose, is a row vector U1 U2 Un. Okay, similarly V transpose is a row vector, is V1 V2 Vn. Okay, so if U and V is defined in this way, we can define the inner product between two vectors this way. Okay, now let's try to realize the geometry of the projection operator. Okay, so we have three vectors U, V and W. Now say we want to project the vector V in the direction of U. So we write down the notation in this way, that is the projection of V in the direction of U. In the suffix we write down the direction. Okay, and this is the vector we want to project, and this is the direction. Okay, now the projection of this vector, this is V and this is U. We want to project this vector V in the direction of U, so the vector would be this one, this guy. Okay, so the vector would be this vector. Okay, so one thing is very much clear from this, that if two vectors are perpendicular, that is, say for an example W here, so the projection would be this vector, that is the zero vector here, because here how we define the projection, we drop a perpendicular line here, and in the perpendicular line touches, say for an example, this point, and the vector from the origin is called as the projection of the V in the direction of U. Similarly, if we want to project this W, the perpendicular vector, and then if we draw the perpendicular line here, so it would give nothing, that is, it would give the zero vector itself. Okay, great. So as notation we can write down U and V, if inner product of U and V equals to 0, if and all leaves U perpendicular to V. This is how we write down the definition. Okay, if U and V is perpendicular to each other, then the inner product between these two vectors are 0. Great. Now let's define the linearly independent vectors. First, say for an example, we have two vectors U and V. We call these two vectors linearly independent if and only if the linear combination of these two vectors C1U plus C2V is 0, implies C1 equals to C2 equals to 0. If this thing happens, then we call the vector U and V is linearly independent. Okay, so for an example, two vectors 1 0 and 0 1. Okay, so if we draw in the x and y axis, one is the unit vector, so this is 1 0, another is another unit vector, so this is 0 1. So these two vectors are linearly independent. How to show that? We take the linear combination of two vectors c of 1 0 plus c2 of 0 1, and according to the definition we'll will write this equation is equals to 0. From here we'll get c1 plus c2 into 0 equals to 0, c1 into 0 plus c2 into 1 equals to 0. So basically we are getting a system of linear equation. We want to solve this equation. Here you can see this c2 into 0 turns out to be 0 itself, which basically gives c1 equals to 0. Here you can see this one is 0, so basically this gives c2 equals to 0. So which basically shows that these two vectors are linearly independent. And one shortcut technique is there. Basically if we are in R2 and if you have two vectors, then you can just compute the corresponding determinant, and if the determinant is non-zero, you can say these two vectors are linearly independent. This is as simple as that. Okay, well, now one thing, see here in this case it was 90-degree perpendicular, right? The two vectors here 1 and 0, 1 0 and 0 1 were perpendicular. Now the general theorem suggests if the two vectors having, so if say for an example, if this is two vectors u and v, and theta is the angle between these two vectors, if theta is not 0 and not pi, that is 180-degree, then we call u and v are linearly independent. Now let's jump into the Gram-Schmidt orthonormalization process. Now actually this process takes an input of linearly independent set, say we call it as S. This is nothing but say v1 v2 up to vk. This take as input. This is linearly independent set, and it gives an output the set of vectors u1 u2 up to uk, where uy perpendicular to uj when I not equals to j. Meaning what? Basically this set every vectors are orthogonal to each other, that is the perpendicular to each other. This is the perpendicular sign. Okay, after that this is called orthogonalization. This step is called orthogonalization step. Okay, so from the linearly independent set we got the orthogonalized vector, and if we divide each of the orthogonalized vector by its corresponding norm, then we get the orthonormalized set. Okay, now this is the whole idea of Gram-Schmidt process. Now let's see how this process is being done. First what we do, we have the given is v1 up to vn. This is the given condition. This is the v1 up to vn, or the v1 up to vk is the linearly independent set. This is given. First what we do, we'll keep v1 as it is. That is, we'll put u1 equals to v1. No change would be there. In the second step, what we do, we'll subtract v2, we'll subtract the projection of v2 in the direction of u1, that is this one, from v2, and we restore in u2. So first step, we'll keep u1 as it is, that is u1 equals to v1. The second step, u2 would be v2 minus the projection operator of v2 in the direction of u1. In the third, for the third vector, the u3 would be similarly the v3 minus the projection of v3 in the direction of the rest two vectors, that is u1 and the u2. You can see after this step you can show that u1 is perpendicular to u2. Just compute the inner product, that is basically v1 and v2 minus proj u1 v2. You can easily see this guy is going to be 0. This one would be u1 v2 u1 u1 into v2. So obviously this is going to be 0. Just calculate it, it would be 0. Check. Okay, so from this two step you can easily check u1 is perpendicular to u2. For the third vector, as I was telling, that u3 would be v3 minus projection of v3 in the direction of u1 minus projection of v3 in the direction of u2. Exactly in the same way that was being done for the vector u2. This is for the u3. And now you can check u1 is perpendicular to u3, u2 is perpendicular to u3 as well. Okay, and we have seen u1 is perpendicular to u2. So u1, u2, u3, both three vectors are perpendicular to each other. Similarly, we will calculate u4, and for the generalized uk vector, this will be calculated in the similar fashion. Now this is the orthogonalized step. That is, we are getting u1, u2 up to uk, where all ui's are perpendicular to uj's when I not equals to j. Okay, now the third step, this is the third step, will divide each u1 by its corresponding norm. That is, we get u1 by dividing u1 by its corresponding norm u1. How the norm was defined? Norm of u1 is nothing but square root of inner product of u1 u1. In my earlier lecture, I have already defined the norm. If you missed that video, I'll request you to go and visit this video. I'll drop the link in the description section. So this is how the norm of the vector u1 is defined. So if you divide u1 by its corresponding norm, you will get the orthonormal vector u1. Okay, and you can easily check that norm of u1, that is the length of u1, equals to 1. How it is that? Length of u1 will be norm of u1 by norm of u1, that is equals to norm of u1 by norm of u1, which is basically 1. So this is the unit vector. Similarly, e2, how we will get e2? We have already got u2. We will divide u2 by its corresponding norm, that is u2, norm u2, and so on. So this is how we'll get u1 up to ek vector. So all the vectors are orthonormalized. So let me recap this whole process once again. We'll give the input as of a linearly independent set v1 up to vk. This process will do such steps and calculate u1 up to uk. After getting u1 up to uk, these are the orthogonalized vectors, that is all the vectors are perpendicular to each other. Then what we do? We'll divide each vectors by its corresponding norm to get the orthonormalized vector. This is how the Gram-Schmidt process works. Now we'll understand the Gram-Schmidt process with a very simple example. Now this example, as we have said, the Gram-Schmidt orthonormalization process takes a linearly independent set as an input and returns back an orthonormalized state, orthonormalized vectors. We start with a linearly independent set this way. So there are two vectors. We call it, this one is v1 and this one as v2. Okay, this one is v1 and this one is v2. Okay, first, as we have said in the first step, v1 would be as it is, that is, we'll just write u1 equals to v1. In the second step, as we have said, u2 will be v2 minus projection of v2 in the direction of u1. How it was calculated? It was v2, v2 would be 2 here, as we have already written down, 2 minus inner product of u1 v2. So how it was defined? It was inner product of u1 v2 by u1 u1 into v2. You can see from the first slide how we have defined the projection operator. Exactly, we have written down here. u1 is 3 1, v2 here is 2 2. So it is inner product of these two vectors 3 1 and 2 2 divided by the inner product between u1 u1, that is inner product between these two vectors 3 1 and 3 1, multiplied by the vector 3 1. If we just calculate this, we'll get this one, this value. So now, as in the second step, we got the vector 3 1 and this vector minus 2 5 and 6 5 as our orthogonal set. This is an orthogonal set. You can easily check by plotting these two vectors in the graph paper, and you can easily see these two vectors are orthogonal to each other. Now, to get the orthonormal set, how to do that? We'll just divide each vector by its corresponding norm. Similarly, we'll do the same thing for the second vector. Let's calculate. For the first vector, say u1 equals to u1 by norm of u1, which is basically 3 1 would be as it is, divided by how the norm was defined. Norm u1 was, we have already said, this is nothing but inner product u1 u1, right? How the inner product was defined? This is 3 1 divided by, so this is 3 1 3 1, the component wise. So this is 3 into 3, that is 3 1 divided by square root of 3 into 3 plus 1 into 1. We will multiply this guy with this guy and this guy with this guy. Okay, that is 1 by root over of 10 into 3 1. Okay, so one can do the same thing for this vector also. So this is how the Gram-Schmidt orthonormalization process is performed. I guess the idea is pretty clear to you. If you have any doubt, let me know in the comment section below. Thank you for attending this class.